Hello everyone, my name is Divyansh Mishra and my group is group number 1 and my group members are Shravan, Divyansh and Shekhar. And first of all, I humbly thanks to Dr. Prasenjit sir who has guided us for this project, and with the help of him we achieved the success in this project. So let's see, we will explain the doubly ended priority queues, and we have implemented that. So let me go further, and what we have done we'll show here. So the table of contents are, first of all we will discuss about the general methods and then specialized structures with which we can implement the doubly ended priority queues, and then how to use how to make or how to implement DEPQ means doubly ended priority queue using a single priority queues, and then DEPQ using min max heaps. And then we'll see that what is property of min max heaps, and then different cases possible using min max heap, and inserting an element, removing an element, and references. So this part will be in part like covered by in part by the members of the group. So doubly ended priority queue, and let me clear it. So inserting an element will be covered by Shravan, and removing an element will be covered by Shekhar. Okay. Now doubly ended priority queue. So what are the primary operations for this? So primary operations are insert, remove max, and remove min. So these three are the primary operations. So why do we need this double ended priority queue? Sometimes we have to remove the first prioritized element, or sometimes the least prioritized element. We don't know which one we have to remove, or uh, like on which we have to control, how to control, and how to control a queue. So and in a single priority queue we have only one axis on either removing minimum or removing maximum. In double ended priority queue we have the privilege for doing the both operations, and insert elements, that is same as that single priority queue. We'll see that how can we insert, remove min and remove max. So general methods, first of all, we can do it by using dual min and max single ended priority queues. Using two single ended priority queue, we can implement this. And the second one is correspondence based min and max single ended priority queues. So correspondence based means there will be some correspondence between the two first priority queue and the second priority queue. So that will be a little complex and will be covered in this video by my friends and my teammates. So what are the specialized structures with which we can implement this doubling priority queue? So that is min-max heaps, symmetric min-max heaps, and deeps, and the last one is interval heaps. We will be mainly focus on min-max heaps. Actually, we have implemented using min-max heaps. Dual single-ended priority queues. How can we implement this double-ended priority queues using dual single-ended priority queues? So this is very simple. That each element in both a min and a max single-ended priority queue, like each element should be present in both the priority queues, in the minimum as well as in the maximum. Here min priority queues means we can remove min, and max single ended priority queue means we can remove max. It means the method remove max is present in the single priority queue, that is max single ended priority queue, right? So I think I'm clear here. And single ended priority queue also must support an arbitrary remove. Here this the second point, arbitrary remove is required because we have to remove one element from the other priority queue. Like if I want to remove a minimum element, then it will be removed in a constant time from minimum single ended priority queue, but it will take n time to search for that element in the max priority queue. So what we have to do is that it should support, the single ended priority queue should support a arbitrary remove operation. Like we can remove any element from anywhere in that single ended priority queue, and each node in a priority queue has a pointer to the node in the other priority queue that has the same element. So this is also an important point, which says that here one minimum priority queue is there, and here a maximum priority queue is there, and the both are having same elements, right? Exactly same elements. So the element in this priority queue should also like point to that same element in the max priority queue, like min to max. There should be a good connection between them, like there should be a pointer which is pointing from each other, so that we can access this element from this one also if I want to remove one of them. And how we will do it using min max heaps. So from here this part will be covered by Shravan, and all the implementation he will show, and then after this Shekhar will take over it. So I'm handing it over to Shravan. Shravan, it's all yours. Thank you.
So in this project, we will going to implement double-ended priority queue with the help of min-max heap. So what is min-max heap? Min-max heap is a complete binary tree with alternating levels being min level and max level. The root level is always a min level, and nodes at min level are known as min nodes, while nodes at max level are known as max nodes. So now properties. So every min node has the property that it is the smallest of the subtree of which it is the root. And same for max node. Like every max node has the property that its value is the largest among the subtree of which it is the root. So there are multiple cases possible. Like if the tree is empty, then there is no min or max level element. And if there is only one element present, then there will be a minimum level with or the min and the max element being the same element. And if the number of nodes are greater than one, then the element in the root is the minimum element, and the max element is one of the up to two children of the root. So now we will going to discuss insertion. So inserting an element. So if the heap is already empty, then we can directly add an element. But we will now going to assume that what happens if the number of nodes is greater than zero. So there is one possibility then that one property can be violated. The min node and max node property can be violated only for the nodes on the path from the root to the parent node. So there are three cases to consider. Parent node being equal to the element which we are going to add now. So in this case, the min and max node properties of all the nodes are are do not getting disturbed by adding the new element. So the properties are satisfied here. Next, the second case, if the parent element is greater than the new element. So in this case, here we are adding 2 and its parent is 20. So this is the case where parent element is greater than the new element. So we will interchange or can say replace with its parent and keep replacing in every min level until it reaches its actual position in the heap. So it got replaced by 20, its parent, and now it will get interchanged also with the root, which is the next minimum level. And since 2 is less than 5, it will get interchanged. And here is the final heap after inserting the new element 2. So now 2 becomes the root node and 5 comes in the next min level and 20 changes its level from min level to max level. Now similar third case, when the parent element is less than the new element. The case when the parent element is a max node is similar, very much similar to this one. In that case, we will compare to the only the max nodes and do the similar processing. It need to be considered only with the max nodes on the path from the root to the parent node. Now we are going to discuss the time complexity for this inserting operation. Since it is complete binary tree, so the height is restricted to the log n. So element inserting an element will take no more than order of log n time. Now I am going to show you a code written for this. So here is the min heap implemented with all its methods, and here is the max heap implemented with all its methods post pop and remove heapify up down. So we are implementing a double-ended priority queue with the help of min and max heap. So in this case, uh, whenever we push an element, it will push to both the heaps, and whenever we remove an element, it will be get removed from both the elements, from both the heaps. So so that it maintains priority, given priority, and the double-ended priority queue property. So here is the example, like we have initiated object of the double-ended priority queue, and we are pushing 1 and 3. Then we are printing, is it empty? Then it is like no, we have pushed two elements. Then we are checking size, which is 2, and then we are getting the min element, which is 1, currently 1, and max element is currently 3, and we are removing minimum element. So here is removing 1 from the 1 and 3. So and then we are getting again the min element, which is now 3, becomes 3, and max element is also 3 because there is only one element in the heap now. And now we are removing the max element, which is 3, and size becomes 0. Thank you.
So, hello everyone. Now we will learn about how to remove minimum element from a minimax heap. So now suppose when there is no element in a heap, means there is no minimum element to remove. And when we have only one element in a minimax heap, means when we remove the minimum element, the heap becomes empty. So suppose that we have uh, number of elements in a heap is greater than 1. So now we need to remove minimum element which is present in a root node. So we need to go from an n element complete binary tree to an n minus 1 complete binary tree. So basically there is two cases to remove a minimum element from a heap. First one is when root has no children. So when we remove the minimum element from a heap, at the same time we will drop the corresponding element which is present in the leaf node on last index. So we have removed, we want to remove 5 from the heap, and at the same time we dropped 30. So now root has no children. So we will update the root node with the 30, means the dropped element become the root node and trickle down process will terminate. Now second case is when root has at least one child. So here we want to remove 5 from the minimax heap. So at the same time we will drop 32 from the heap and put it to the root node. So here is the updated structure of heap, but this structure does not following the rule of minimax heap because the minimum element must be present on the root node, but the 22 does not the minimum element in a heap. So to find the minimum element, we follow the left path from the root node and we find the minimum element which is present in a minimum layer of the heap. So here is 10 is the minimum element and we will replace it with the 22. Now here again there is the updated version of minimax heap structure, but this structure also does not following the minimax heap property because 22% in a minimum layer means the both the children of 22 must be greater than 22, but the both the children of 22 does not greater than 22. So here we will follow the trickle down process and update the heap structure. So here is updated heap structure which is follows all the rule of minimax heap. So now here are some references we have used for this slides. Thank you.